Uh, Welcome back to this today's plenary session. It is an honor and a pleasure to introduce Dr. Rajeevan. He's currently a professor at Atria University. He has been associated with the Ministry of Earth Sciences in the capacity of secretary to the minister. But we know him for some time as a kind of keen researcher in monsoon prediction. Thanks a lot, Dr. Rajeevan, for accepting our invitation to offer a plenary lecture on monsoon predictions. Thank you.
Thank you. Yeah, thank you for Vishal for nice introduction. But only thing I just want to correct, I was not secretary to the minister, but I was secretary to the government of India. Yeah. There's a big difference between secretary to the minister and secretary to the government. Sorry, yeah, fine. So I thank you, Vishal, for inviting me for giving this talk on challenges in monsoon prediction. So as he was mentioning that I have been working on this monsoon prediction problem for many years. So I'll, how much I should spend? 50? 50, fine. So, okay. So this is the broad outline of my talk. I'll just talk about a little bit on the theories of monsoons, a very little bit, and variability. And so as far as the monsoon prediction is concerned, so you can have monsoon in short range prediction, you can have extended range prediction, you can have decadal, you can have seasonal, but what I will be talking is only on seasonal prediction. And so I'll be talking about what is the premise of seasonal forecast, a little bit of history of seasonal forecast that Vishal wanted me to talk about the old statistical model, how we evolved and why we wanted a dynamical prediction system. So old statistical forecasting methods, and then how we moved to dynamical methods and what are the limitations of our dynamical methods and limits of seasonal predictability and what we should expect as a future prospects. So this is very famous figure. You can see that between January and July, there's a big changes in the winds as well as the SSTs. In the north, in the top one, you can see that SSTs are warmer in the close to equator. But when July comes, there's a warm region here as well as warm region over Bay of Bengal. The Bay of Bengal also gets warmed up. And this 200 is nothing but it's OLR, outgoing long-wave radiation. So convection, instead of convection being within the equator, just close to equator, just moves in northern parts of Bay of Bengal by July. So this is the reversal of winds. So this is the circulation pattern associated with the monsoon. And so there are theories of, briefly I'll mention about, the first one was, what do you mean by monsoon and how the monsoon is defined? There are a lot of theories. And first was Halley. He said that basically the annual cycle of monsoon circulation is nothing but because of the differential heating between ocean and land. Because land during summer, it gets heated up much faster than ocean. So there's a temperature gradient. So accordingly, there will be a pressure gradient. So wind circulation will get also reversed. And Hadley, 1735, proposed that the same concept, the so-called temperature contrast, but then he said that Earth's rotation plays an important role, Coriolis force. So that's why we get, instead of southerly wind, we get southwesterly winds. And Webster later suggested that, proposed that moist process, basically the latent heat, is an important component in monsoon circulation. That's all we know now very well. So the whole discussion on this workshop is basically moist convection. So it's a right kind of problem which you are discussing it. So if you assume that this simple land sea contrast, this right hand side, this figure will work. So around 20 degree north, the wind goes up. There's an ascending motion, comes back and descends over here. There's a huge, gigantic sea breeze circulation because of the thermal contrast between land and ocean. So we call it reverse Hartley circulation instead of Hartley circulation, which is ascends over the equator. Here the ascending is over around 20 degree north. And so, but this concept of land sea temperature contrast and sea breeze concept, circulation concept is not well accepted nowadays because there are a lot of problems of accepting it. There are a lot of issues. It can be, at the first instant, can be a good explanation how the monsoon is. but it will not explain the monsoon variability, especially monsoon variability, it cannot explain. I can give an example. So this is the famous plot which shows that when after the monsoon sets in, if you really see the temperature and how the IS monsoon rainfall, you can see that when drought happens or when low temperature happens, the temperatures are, so low rainfall happens, temperatures are much higher. So a higher temperature doesn't mean that you will get more rainfall. Okay, once monsoon sets in, the circulation gets in, monsoon circulation gets in, clouds form, rain process starts, so then temperature doesn't have any role to play, the so-called temperature contrast. So in many research papers, now when you read, if you really want to explain the decadal variability or anything related to monsoon variability, they take the word land-sea contrast and explain in terms of land-sea contrast. There are some problems associated with that, especially with aerosol. They say that aerosol is contributing the reduction in the land sea temperature contrast, and that could be the problem of monsoon variability. Frankly speaking, it's not really a good theory to propose. And as a researcher, I will tell you, I will recommend that you should be brave enough to give a hypothesis in any research. And it is not your responsibility to prove that you are right. Somebody else will prove that you are wrong. Till then, your hypothesis will remain correct. Okay, so you have brave mind and always make a hypothesis. So the basic concept now, the monsoon concept, I think, talk in terms of northward propagation of ITCZ. It's a very simple concept. It can explain many aspects of monsoon and mean monsoon as well as the monsoon variability. And this is a plot shows where precipitation exceeds surface evaporation during boreal summer and austral summer. And so you can see that these are the places where we get monsoon, and these are the places, and this is North African monsoon, this is South Asia, this is East Asia, West Pacific monsoon, this is Australian monsoon, the South American, North American. So you can explain the monsoon in terms of northward propagation of or southward propagation of ITCZ. So this is the basic concept of global monsoon has come very recently after the famous paper by Bin Wang et al. 2011. It's a new concept of global monsoon system. So you can define monsoon not regionally, also you can define in terms of a global concept. So the criteria is if summer minus winter precipitation exceeds up 2.5 millimeter per day, and local summer precipitation exceeds 55% of the annual total. So, and these are the regions where we can expect this kind of criteria. So you have South Asian monsoon, East Asia, West Pacific, the North American monsoon, South American monsoon, Australia. We have North African monsoon and South African monsoon. And out of that, we know that South Asian monsoon is the most important and most strongest, probably the strongest monsoon we have. And many years back, Asian monsoon is nothing but it is South Asian monsoon. So East Asia monsoon, the concept, everything has come very recently. So South Asia plays an important role in monsoon system. Okay, so this is the monsoon rainfall. This is from IISc data. So you can see that this is the mean pattern, and this is also the coefficient of variation. This is all well known, so I need not really go into details. So monsoon variability, you know that at any place the monsoon varies in different time scales, starting from diurnal and then goes to synoptic, then intra-seasonal, so intra-annual, and even multi-decadal. So monsoon has a variability in all spectral bands, and the diurnal is nothing but in a particular day, the rainfall doesn't occur all the 24 hours, it occurs at a specific time. So it varies from place to place, and some places, for example, if you see the foothills of Himalayas, here it is in the early morning, the peak, monsoon rainfall peak comes in the early morning, whereas in the eastern parts of central India, northern parts of the country, it is in the afternoon. So basically afternoon means afternoon heating, that contributes to convection and more rainfall, whereas in Himalayas, close to Himalaya, foothills of Himalayas in the early morning, that is nothing but the early morning, what happens, the katabatic winds flows from the hills, and there's a monsoon flow, it both gets together, and you get a lot of convection there. So what I mean to say that monsoon exhibits strong diurnal variation. And also there is a diurnal variation of Bay of Bengal. It starts from here, it goes down. It propagates to south. Okay, And this is the monsoon precipitation associated with the monsoon lows and depressions. So this is on synoptic time scale, 3 to 5 days time scale. And this is rainfall associated with the depression. And this is associated with the low pressure, which are not really of depression. You can see that the depression, the rainfall is confined to a very narrow region, the more focused rainfall, whereas low pressure system can give rain anywhere. Okay, so lows and depressions are main synoptic systems which contribute to monsoon rainfall. And if you really take a time series rainfall data and do the spectral analysis, you get a lot of high spectral values, 32 up, so 10 to 60 days time scale, it's in a lower 10 to 20 days, then 30 to 40-day time scale. There are two bands. 10 to 20-day oscillation is a westward propagating mode, closely associated with the monsoon active and break condition. And also this is 30 to 60 days. So some people associate with this MJU and all these things. So there is a strong intrasystem variability, which I will not go in detail. I will not talk about it. And during the associated with the intrasystem variability, we have a beautiful concept called active spells. This is rainfall associated with active spells. And there's a clear definition of active spell. What do you mean by active spell? And also there is a definition of break spell. So this is just opposite of, you can see just a polar. You have a lot of less rainfall during active, less rainfall here, but in break you get more rain here and more rain here. But less rainfall, basically West Coast as well as just opposite phase. However, there are theories why it happened. There are also mechanisms why we should have this kind of rainfall distribution. And this is the year-to-year variability. It's a well-known pictures from 1875 to almost 2020. Monsoon rainfall doesn't have a long-term trend. So monsoon is basically a robust system, but it has a large year-to-year variability. These reds are basically called the droughts, and greens are flood years, and in between there are normal years. So, and you can also see that there is an epoch in which you have more number of years of drought years here. And again, there is a spell, there's an epoch here, and not many droughts. And again, another spell in which you have more droughts. And also again, we had another spell. So if you really plot a 31-year running mean, you get some kind of this kind of graph. It's very famous plot. And you have low rainfall epoch, high rainfall epoch, low rainfall epoch, and again. So when this rainfall epoch, when 31-year running mean, when started moving up, we all thought that we are all going into a positive phase. There's a lot of celebration. There's a lot of discussion. Still, I remember, but it did not happen. The question is why? Again, it came down. So again, it is picking up. So hopefully, we are going into a positive phase. And why monsoon is important? Because monsoon anomalies, rainfall anomaly, if you really plot with the Indian GDP, it has a strong relationship. Any rainfall, so but it's very interesting. It's not very linear. It is non-linear, and the effect of low rainfall on droughts on a lower deficiency scale is much more impactful on GDP than when you get excess rainfall. So excess rainfall really doesn't contribute to much more than GDP, but a drought definitely plays an important role in pulling down the Indian GDP. Question is why? And one reason could be more, we don't know how to make use of the excess rainfall into, basically Indian GDP, it affects Indian GDP through agriculture mostly, and agriculture, then service, etc. So then a drought can really pull down the agriculture crop output, and it can really affect. Whereas excess rainfall doesn't really contribute to that excess crop production. So we don't know how to make use of. That could be one explanation, but I don't know many. There could be many. And we know how the monsoons, internal variabilities influence, and so it's one of the major influence. Probably Arinda must have talked to you yesterday that the teleconnections, etc. So, but then we also know that there are exceptions. For example, 1997 was one of the worst El Nino we had. Most severe El Nino, but then we had still under 2% of normal. We had good monsoon. Whereas in 2002, the El Nino was not so big, but then still we have large deficiency of monsoon rainfall. And the question is, you can see the pattern of monsoon El Nino's SST pattern. It's more of canonical El Nino, and this is more of a Central Pacific El Nino. So there's a Modaki or whatever you call. So it's not very simple. The relationship is not very simple. That's what I want to highlight. And if you really put a statistics of so many years, 1870 to 2024, when El Nino occurs, we know that most of the very high probability that you will have end up with a deficient rainfall. But also you see that there are years in which we had normal rain. So getting out of 32 years of El Nino, we had droughts only on 16 years, in 16 years. It's only half, 50% probability. Whereas there is a high probability that they do not have a excess monsoon. You cannot expect, when El Nino happens, we cannot expect a excess monsoon. Similarly, for La Nina also, it's not very simple. You can expect that in La Nina, you cannot have a drought. It's almost confirmed. But there are many, out of 23 years, only 9 years it is excess. So the relationship is good, but it's not as simple as what we think. And also the recent studies by Sulojana and Francis, etc., have come up with the relationship between the Indian Ocean. You may all must be knowing the Indian Ocean dipole. This is something related to Indian Ocean dipole, but in terms of, you can see that the sign of rainfall here, OLR here, and sign of OLR here, anomalies are all same. So that means West Indian Ocean is associated positively with India, whereas negative East Indian Ocean is negatively correlated. So this is the kind of a dipole pattern. So she calls it a kind of oscillation on the surface veins, close to surface veins, and that also plays an important role. But this has a simultaneous relationship. It only happens during the season. And another, as I told that in all, there are years in which we had droughts without El Nino. And there are El Ninos, but we did not have droughts. So all these things we should know. And also we should know why, how, and all these things. So the question is, in a non-El Nino year, how a drought happens. So one theory, recent paper is from IISc Bangalore people. So this is the SST anomaly with the El Nino drought. And this is the SST anomaly with the non-El Nino drought. And you can see that there is no El Nino component here. So but where here is all beautiful El Nino component is there. But what we see is the anomalies here in the Atlantic. So what the paper says that, also when we developed model, I will tell you a little later, the Atlantic Ocean also plays an important role, especially in a drought which happens without El Nino. And the physical mechanism is that you create a positive kind of SST anomaly here can really produce the kind of Rossby wave pattern along the middle latitudes, and that can really pull down monsoon, and especially in the second half of monsoon. So, for example, a year like 1979 was a severe drought, but it happened during a non-El Nino year. And first half of monsoon was so good, second half was very bad. So that's a beautiful explanation of why 79 was a drought. And this is a decadal variable. As I told that, I will not go in detail, but there is a beautiful multi-decadal variability in Indian monsoon rainfall. And there are papers suggesting that what could be the mechanism. So we identified 4 regions. This is a typical decadal El Nino. We have Indian Ocean. We have North Pacific. It's basically the interdecadal ENSO and the AMO. AMO is somewhere here from the Atlantic Ocean. And there is an interdecadal ENSO. So there are 2 interdecadals, sorry. And this is from PDO, and this is a basinoid view. So Pacific decadal oscillation also plays an important role. So there are 4 regions where they exert variability, decadal timescale variability. So I'll go into the seasonal forecast, which was my bread and butter for many years. And so I will go in detail. So if you really see the predictability, if you really see the forecast skill with the time, you can see that our day-to-day forecast, next few days, short-range forecast, sharply comes down after maybe 8-10 days. It doesn't have a skill beyond 8-10 days. Then there's a skill somewhere here, which we are making use of it now for so-called S2S prediction, especially on an intra-seasonal time scale. Then we have a seasonal forecast. There's a predictability here, and also in the climate projection time scale. Now, the recent research has come of annual to decadal kind of prediction. So it's a new concept which is coming out. A lot of work is being done. And I thought initially I'll talk about it, but I need a lot of time for that. But you should know that there's a lot of work is going on this time scale. So this will be well known, weather predictions we know, and intra-season also a lot of work has been done. And what I am going to talk is this. And So question is, if so-called theory of chaos, if you accept it, then you cannot predict more than 7 8 days in tropics, then how you predict seasonal forecasts? How you make seasonal forecasts into a season, into advance? The basic reason is that in seasonal time scale, there are variations in the last oceans, for example, sea ice, etc., which have a longer time scale, which goes well with the monsoon variability. So if you really know how the SSTs are behaving, sea ice is behaving, snow cover is behaving, we can predict at seasonal time scale. The slow varying boundary conditions. And traditionally, so IMD started first monsoon forecast in 1886 because 1870 they started IMD in 1875. Within a couple of years, they had 2-3 droughts. So started with a bad woman. They started with a bad many droughts. So then they said that we should have monsoon forecast. So India was the first country to start monsoon forecast in 1886, based on the relationship between Indian monsoon and snow cover over Himalayas. They thought more snow, less monsoon, because it basically reduces the temperature. So the concept. So the physics, the idea of physics was there at that even 1880s. So okay, so that was the first paper. It's for Blandford, 1886. And then in 2016, under monsoon mission, we started a coupled forecast system at 38 kilometer. And NCMRWF also started. Then we have now coupled climate prediction models, the state of art models now, which we talk about. So I'll describe the details about it. So he was the person who really started monsoon forecast in a very systematic way, Sir Gilbert Walker. You may be knowing about Gilbert Walker circulation, etc. He was the DG of IMD for many years. And basically, he was a mathematician. So he first applied regression method approach for moral, and it was being followed by IMD for many, many, many years. And so he was a really intelligent guy. You may not be knowing, he's the person who nominated C.V. Raman for Nobel Prize. We had good people in IMD at that time, even now. Okay, so we did an exercise of monsoon forecast, Suluzna got Gilles, Rajeevan, and everything. It's a very famous paper. It came in 2005 as in climate science. 2002 was a drought. Then within 2 years, 2004 also was a drought. And many people asked, why your forecasts are going bad? Even by the time I was in charge of monsoon forecast in IMD. So many people ask questions. So especially press and media, government asked, why you are monsoon forecast? So we really wanted to know what really happening. So earlier in the Bacchus time, they used to give forecast for 2 regions. One is Peninsula and one is Northwest India. He was very clever. He was knowing the predictability of Northeast region is very poor, even now. So he never attempted to make a forecast for Northeast region. Okay, so he attempted only 2 regions. So it was all manuscript form, 1920s forecast, 30s forecast. It was lying here and there. I took a lot of care and tried to assimilate all the models, all the data, and tried to do it. You can see that correlations are pretty poor. Minus 0.4, minus 0.10. And if you take all international, a little bit correlation. And what you do is here is the error in terms of observed rainfall. That means actual minus the forecast. And you can see that it has a strong bias in both drought years as well as excess years. The excess years, it doesn't predict that amount. Drought years, it doesn't predict that kind of deficiency. So extremes are not well predicted. But it's good in normal monsoon rainfall forecast. So, and we wrote a paper and we told this could be the reason. And this, I'll tell you a small story about it. When this paper published, Jairam Ramesh was MP at that time. So he took this paper and went to the parliament and said, top 3 monsoon meteorology is saying that your monsoon forecasts are bad. What the government is doing? Kapil Sibal was the minister. Kapil Sibal took it another way. He said, and that is the story goes, but I'm not very sure, but this is the story goes. He told in the parliament, we know that our forecasts are not good, so we need money for investment. That is the beginning of the first modernization project of IMD with 500 crore. So my point is that science can really pull down or pull up the policy issues of the government. So we should write good papers to influence policymakers, and we should be bold enough to tell the people that this is the way it is going. It should be helpful. So this paper was very famous, but we could not do anything. We only told our monsoon forecasts are bad. So government said, you take this 500 crore rupees and improve it. That is the beginning of the modernization of IMD. Good. So Elis Monsoon, there's a famous paper by Carson. So she's basically from UK. She wrote a very detailed review paper on monsoon forecast. And what she said that during the period 1886 to 1953, there was a famous review paper by Norman. You must be knowing about Norman. He was a DG of IMD. So he wrote a paper in 1954 or so, says that IMD continuously revised the methods of prediction using different predictors. However, all the methods failed to achieve the accurate prediction. And also it was mentioned, nevertheless, the imperatives of economic administration, empire, and public demand compelled IMD scientists to continue annual publication of seasonal forecasts. So in spite of all failures, government has decided we should do the monsoon forecast. So monsoon forecasts are still going on from 1886. In no year, we did not issue forecasts. All the years, forecasts are issued. Irrespective whether the forecast was failed last year, and continuously it was failing, we did not bother about it. We kept issuing forecasts. And it's a very famous paper. It's by Gaurikar. Gaurikar was chief scientist, the big man in ISRO. Then he was the vice chancellor of Pune University. And he developed, he and his group, Taplial, basically, he was my boss at IMD when I joined IMD. And they developed a power regression model for long-range forecast. So power regression, they used 16 parameters around the globe. And so this was the equation they formed. So it's not a linear equation. It's because there is a PI, power, and this is also a constant here. And this alpha, B, and R just basing a kind of a factor which, for example, 1000 is pressure is in 1000 scale if you really want to divide it and make it into small number. So these are all, but basically your CAs and PAs are there. What they did is, there are 33 unknowns. So there is a C0. So, and 16 means 32 here and 1 plus 33 unknowns of C and P, but model was trained with just 30 years of data. So if you really give it to as a problem, it's an ill-defined problem. You cannot really develop a regression equation of 33 unknowns with 30 years of data, but they did. And the model was in execution, model was in operational mode for almost 16, 17 years. Unfortunately, what happened means the model, during those years, the monsoon rainfall always was normal. From 89 onwards to 2002, 2001. 2002 was a drought. So up to all these years, the monsoon rainfall was normal, and this model was predicting normal. So people all thought that the model is really doing wonder. So when the first drought came 2002, the model did not say anything. 2004 also, model did not say anything. So that was the period I was asked to change this model. And there was a lot of inertia in our government system. Don't quote me, but anyway, it's out now. I am no more in the system, so I can always say. So we have, government has a lot of inertia. If it is going, let it go, that kind of answer. And especially if big people like Vasant Gaurikar is involved, they don't want to change the model. They knew that science is bad, we cannot really do, we need changes. There was a big inertia. So when if you really read the paper, you get unrealistic correlation of more than 0.9. So if somebody comes with a model of correlation 0.9, you don't read the paper. You assume that the model was fitted with overfitting, and the answer is wrong. Your model is wrong. So people will normally write papers, oh, my model has a correlation of 0.9. That really says that your model is not good. Okay, so, okay, good. Okay, so this is the scatter plot between actual and forecast for independent period for 1989. So model, the dependent period, when the model was trained, the correlation was 0.9 or more. But during independent, you can say it is it's close to 0. There's nothing. So that was period when we tried to develop a new prediction system, ensemble statistical prediction system. And so one of the basic problems in statistical prediction system is the so-called secular variation of the teleconnections. Probably Arinda must have told what are the different teleconnections. If you take a parameter and correlate, you take a 30 years of data, you get a correlation. But you shift it to another 30 years, you may not get the same kind of correlation. There's a secular variation in the relationship between these. The question is, if the relationship is physically disconnected, why it should change? Okay, why the correlation should change? The answer could be the correlation is nothing but the covariance divided by the standard deviation of two things. So the covariation can change, it may remain same, but if the standard deviations of each x and y is changing with different time periods, correlation can change, isn't it? But the physics can remain same, but the number it can really change. So we need, in the statistical model, we need predictors with some statistical correlation. Otherwise, we cannot really do it in the model. You cannot develop a model. And of course, with the AML now, probably you can use it. Even if you don't have a correlation, you can use it, but not in the typical statistical model. So then we had tough problem of, this is the parameters which they used in 16 parameter. You can see that this is a 21 running means, all are good, but recent years, during those recent years, our correlations are pretty bad. So then we try to develop a new model with these are the new predictors which we identified. And basically, it is, you can see the predictors are from here. Basically from Pacific, so that means the relationship with the El Nino, and also there is a relationship with the East Asian pressure, and this Atlantic Ocean, which I told the Atlantic Ocean plays important role. So there are two indices from Atlantic Ocean. There is one predictor from North Europe. It's nothing but it is related to North Atlantic oscillation. And so these are some of the predictors which we use. And this one warm water volume, we used it. So warm water volume is nothing but it's a precursor for El Nino event. But before the El Nino event happens, the West Pacific, the whole ocean gets warmed up. And if you really calculate the heat content over that region, it will be very high, very high. So if you can monitor that heat content over that region, you can see that after a few months, it will get discharged and you get an El Nino event. So if you need not wait for July, August to see the El Nino is developing it, by February, March itself, you can get a signal from West Pacific. So that was the paper I wrote with a person called McFadden, who's a very famous oceanographer. So these are the two methods we use. One linear method, simple multiple regression, and use a non-linear, it's called pursuit projection regression method using these predictors. And what we did is, normally in the model, what we do is you take 5 predictors, you use all 5 predictors in the model, multiple regression model. It's very simple, you use it. But these 5 predictors may be intercorrelated. So if we really use it, it may really spoil the model. So what we did is, assume that we have 6 predictors, you can have a model with 1 predictor. Like that, there are 6 models. You can have predictors with 2 models. You can have a model with 3 predictors. You can have a model with 4 predictors. You can have 6 predictors. So if you have n number of predictors, you can have 2 raised to n minus 1 models. So what we did is, we did not use one model. We use multiple 2 raised to n minus 1 model. One is linear model, one is non-linear model. Then that's why we call ensemble system. And so this is all possible models we use. And after that, we select best 6 models from here and 6 models from here. Then you calculate a mean forecast. So that is the ensemble system which we done. So we did not depend on only one parameter. The question is how you select the 6 model. This is the question. So I will just briefly mention. So what we used a method called generalized cross validation. So this is a formula which we use. And we have 2 data sets, one for April, one for May forecast. And you can see that if you really plot rank of the model with the GCB, and you can see that there are steps. You can see a few models are here, then there's a step here, another step here, another step here. So there are epochs, there are kind of sets. Similarly, here you can see that first 13 is one way, another is just a jump, then again jump, again jump. So these are all pockets. So then what we do is we calculate the RMSE with the number of models with that, or the two sets. And you can see in the first set, by 4th or 5th models, the RMSE reduces. But any addition of any parameter more, any model more, it doesn't really reduce the RMSE, but it really increases the RMSE. Similarly, in the set of 3, up to 13 you can go, the model can really, so the RMSE can go down up to 13 models, but not beyond that. So we stop at 4 here, and we stop at 13 here. So that's why the best models are selected. And this is the results. These are independent data sets. Real forecast, not experimental, real-time forecast, which we gave to the government. Pretty good. When you see here, and this scatter plot and this scatter plots, there's much difference. At least the correlations are now positive, so close to 0.55 or so. So pretty good forecast we have. And even this year, actual rainfall of 108, the model was predicting 106. So it's a pretty good forecast. It's a statistical forecast system. Okay, so this is some statistics. You can say that initially the correlation was minus, then the new model then 0.55, the absolute is 7.26, 5.64, 7.28, it can is 8.84. This is a standard deviation. So if you really divide this, that you get this number. So this number should be small. When you really calculate the standard absolute error, when compared to standard deviation, it should be very small. Okay, so but IMD is limited. There are statistical model limitations. One is, still model. I will tell that there's a limited skill of extremes, especially in droughts. Limited scope. You can go to up to all India rainfall. If you go for a small region, statistical model really don't do well. Then constraints due to secular variation of predictor rainfall relationships, nonlinear relationship of the predictors, limited understanding of observed monsoon variability, and user demands forecast on a high resolution. If you really go to the government and ask them what you want, they say that we want forecast at state level, district level, which the premise of seasonal forecast doesn't allow you. The basic theory, if you really see the first paper of Charni and Shukla paper, which thought about the premise of seasonal forecast, why seasonal forecast is possible, very famous work, 1981 or so, Charni and Shukla. They say that a monsoon rainfall average over large region, over longer period is predictable. Okay, so that's the premise of season. So that's why we are trying to do 4 months average and all India average. If we really want to go forecast for a small state or district, really doesn't come under the seasonal forecast premise. So we may be able to do it, but we are not sure. So then when we thought dynamical model is a better option. So that's why we moved to dynamical prediction system. I'm not praising it, but I'll tell you the first dynamical prediction system in India was developed by IMD, not IITM, IMD. IITM. So I knew, sorry, I should not say take my credit, but then we knew, I should say we, not I, we knew that statistical model had limitation, so we should move on to develop a dynamical prediction system. When I really wanted to do it, there are a lot of opposition within IMD because they have been thinking only Walker, Gaurikar, they cannot think beyond. So when I said the dynamical model system, they said, how? First of all, you need a model, number one. You need a computer to run it. Everything was done. This was first forecast we did. Ravi is not here. Ravi is the person who really helped me to install the model in our computer. We bought a 6 crore machine, silicon. At that time, it was silicon graphics. So we spent at that time around 60 lakh. 60 lakh, now it is equivalent to 6 crore. 60 lakh, we bought a machine in Pune office. And we put the model, we installed the model called seasonal forecast model of NSEP. So that was an official model of NSEP at that time, US. So it was developed by a person called Kanamitsu. It's a very famous person, Kanamitsu. So that model was hired by us, and people like Rajan Kumar and all helped me to get the model. And Ravi Nanjundaya came to Pune and he helped me to install this model. So this was in 2006. And this was the forecast for 2009, which was a drought. You see, it was not so bad. You see the West Coast, everything was red, the model. And this is an atmospheric model. It's not a coupled model. At that time, seasonal forecast model is an atmospheric model. So when you really want to run for the future, you can do 2 ways. One is you assume that SST anomalies are persisting. For example, you assume take May SST anomalies and assume that their SST anomalies will remain same for the next 4 months. Actual SST will vary because you have to impose it to the climatology. But anomalies will remain same. It's called persistent anomaly method. The second way of doing it, you use some ocean model and predict these SSTs for next 4 months and use that. Either of this you can do. But then you need an ocean model to develop it. Okay. So, but we used to have this persistent anomaly method for many years. So this SFM model was developed for, used for many years. And the first seasonal prediction, a kind of inter-comparison was done by Sulojana Gadgil and Srinivasan with the CDAC computer. So these are the people who developed, who are involved. There's NAL here, IMD, IISc. IMD, IISc means our group, NCMR WF, and IIT Pune. And so the results show that none of the models were able to simulate the correct sign of the anomaly of the Indian summer monsoon rainfall for all the 4 years. So this was done in somewhere in 2010 or so, I think 2010. So it was a big experiment. It was supported by DST. So then this was the result which we got. So we know that 2010, models are not pretty good for seasonal forecasts. Even though we knew that dynamic models are pretty good, we need to go to the dynamic model to get the good seasonal forecast. But at that time, we know that models are not good. Okay, that's why we persisted with statistical model for many more years, still even after 2011. These are the, so what we did is, this was a very famous paper by me. So what I try to do is, if I try to, whenever the new models comes, we try to see models are good, so that we can use it. So a kind of a testing the model. So around the beginning of 2010, there was this new system called Ensemble Prediction System. It was developed by UK group, European Union group. And so that model is, this is the absurd climatology. And this is the rainfall climatology from ECNW seasonal forecast in 2010. You see here, there is no monsoon. Even the mean pattern, forget about variability and all, there's no mean pattern, there's no monsoon on that model. Then into the ECMWF, ensemble prediction system, multi-model climatology is very good. Very good. Sharp improvement in the couple, these are our coupled models. These are all basic, these are also old atmospheric model. So there's a significant improvement. So that then I wrote the paper. I told that dynamical model prediction system is improving. That's a statement I made, and we should focus and we should do it also. So that was the paper. And 2012, this was the examples I give. So if you really see the earlier version of the model 1979 to 99, you really see the correlation. So of course you get a lot of correlation in the Pacific, which is well known. But over the Indian region, South Asian region, there's hardly any red color. But when you really take the ensembles, there are a lot of red colors have come. So I told things are improving. So that's the beginning of the coupled model system. And this is how the forecast is the mean pattern. And what we can do is we can also calculate for two different periods. I calculate the skill. Skill is nothing but correlation with absolute data. And also from the, because you have ensemble members, you can calculate the so-called the potential predictability from the model. It can vary from model to model. So depending upon for this model, for this period, this was the potential predictability. That means you correlate among the members. So that is the potential predictability. And if we take the recent years, this is the prediction. So what we wrote in that paper is the actual model skill is very close to the potential predictability, but still lower. But in the second period, the recent periods, it is much, much lower. So that means we have skill, but it's still lower than the so-called the potential predictability of monsoon rainfall. So then we had 2017, we developed this monsoon prediction system. Probably today Surya Chandra Rao must have talked to you about this. So this is also a beautiful, it's basically NSUB model, version 2. We put it into 38-kilometer resolution, and we try to develop this model. So this is also a pretty good model system. Still, it is working, and a lot of papers have come. So at that time, what we did is we chose a lot of models which was available at that time and tried to get the correlation. It's a Taylor plot, and we found that the NSUB CFS2 version 2 was much better than many other models. That's the reason we focused on that model. We developed that. We adopted that model for developing. Then they did a lot of research. Of course, people like Partha also was involved in improving the physics part of this model, and things are improving. So now but this model has systematic errors. I'll tell you, this is the dry bias, which is well known. Take any coupled models, including CMIP models also, all the CMIP models, even CMIP 6 models, there's a dry bias over Indian region. The model predict less than what actual observation. And it predicts more over Indian Ocean. And also there are biases here. So you have some so-called double ITCZ and all this kind of problems are there in the model. And if you really see the correlation, the skill score of spatial pattern, it's not bad, not so bad. You can see except over this region is all negative, but you get more central India, to some extent South Peninsula, the correlations are pretty good. The model has really good skill, 81 to 2022 correlations. I know these are significant, 90%. You can see that model has good skill. Yeah. Yeah, this is a time series. You can see that the 2009 and all was well predicted, but 2015 to some extent. This 2015 not so good, but 14 it was good. So this is a skill. And they recently brought out a new version, second version of MFCF's model. So where they used a new ocean model. The model was ocean component was changed. And they brought the new ocean model. Still the problems are there. There's a dry bias here. You can see that the bias is here. Still here, the bias is here. Even the version 2 biases are here. Any questions? You asked Nandi? No. So the biases are still there even in the second version of the model. But they claim that the seasonal forecast skill has improved. Really plot the GPCB and MFCF's model. The first version of the model, this is a scatter plot. And if you really see the second version, the model is, you can see the scatter is a little more close and narrow. And so you have better skill in the new model. And that is seen here in the Taylor forecast, Taylor diagram. This is the latest version. You can see that they claim that forecast skill is about 0.7, which is pretty good. I showed in ensemble model it was 0.55. So they then even in ensemble the Monsoon mission model first version was close to 0.55 to 0.6. Now they say it is 0.7. And this is, still there are biases. This is observed. So this is the correlation coefficient between monsoon rainfall and the SSTs. You can see that this is observations. But over in the model, you can see this strong for with the El Nino. I'm saying, sorry, it's not SSTs. So what you can see that over Indian region, the SST correlations are much stronger than the observed. So this is a serious problem. Even in version 2 also the problem still remains same. So it's not much change. So that means in the actual observations, the correlation between El Nino and monsoon is not that strong. It's strong, but it's not strong. But in the model, it's much more stronger. So what happens is when El Nino happens, the model responds very severely. The model immediately says that if a drought, it's going to be a drought. Okay, it need not be a drought. So that's a problem. So we need to really work out that the stronger correlations. And we have another new set, some models also came out recently, so-called North American multi-model ensemble. So this also have the same kind of, you can see the same kind of correlations are there. So this system also is pretty good. So there is a skill in the equatorial region, but over Indian region also the skill is not that bad. And this was the time then we wrote, dynamical models have better skill than statistical model. That's the first time we wrote in the paper. Again, Taylor diagram. Then recently, 2021, before I retired as secretary, then we developed a new prediction system in IMD. What we tried to do is we took a lot of models from different, WMO has a seasonal forecasting framework in which they ask all people, prediction centers to develop seasonal forecasts and give it to them. So they put it in a website that is managed by Australia. And so these data forecasts are available. It's a real-time forecast. So we try to use those forecasts. And it's all red color are models which we have chosen. And then we developed a multi-model in some prediction system for different time scale, also different lead time. So you can see that this is the correlations of multi-model ensemble system. What you can see that the correlations are good here, correlations good here. But still I highlight the poor correlation over this region. This is so-called monsoon core region. So models have still problems of getting good correlation over the monsoon core region. And I'll tell you the variability of monsoon core region is much more important than any other region. And if you really take a correlation between rainfall over that region and all India rainfall, you get correlation of close to minus 0.9. That means the whole all India monsoon variability comes from the variability of that monsoon core region. And also very important because most of the agriculture output comes from there. Rice, wheat, everything comes from that region. So that region is very important. But unfortunately, the models are showing that forecasts are not good, that monsoon core region. And this is another new method called index of agreement. This is the formula. And so there also you can easily the correlation, index of agreement is very poor over monsoon core region. The question is why? And also I showed that the model does have a strong dry bias over this region. So the question is whether the strong dry bias of the models is the primary cause for this is not well known. So we need to understand why the models have showing a poor skill over the monsoon core region. And I personally feel it should really improve over that region than any other region. Okay. So if you really take all India correlation, it comes up. But we know that the correlation, a good skill comes from here and here, not from here. Okay. To tell the government, we can take an average and tell to the government, so correlations are good, but we should know that the skill is coming from somewhere else. It's not really, frankly speaking, it's not really useful. And this was, last year, 2024 forecast is pretty good. This was actual observed rainfall in June, and we know that June was not good. And the model was able to predict, these are three different criteria, different categories. You can see that northern parts, we expected that monsoon rainfall will not be good, but over South Peninsula, we expected monsoon rainfall is good. So models are doing well, but there are exceptions. So, and this is one famous paper by Ramu. I think Ramu is your group. Surya's group. So what he tried to do is he tried to use many models and try to develop a kind of a tables in which but the models are good in predicting the extremes. Forget about correlations, RMSE. The models are able to predict the extreme. Things are not good. Out of 17 extreme years, I'll talk about only CFS V2. It's got monsoon mission model, predicted only 7 extremes in February initial conditions and 9 extremes in May. So it's not that good. So models are still have problems in predicting extreme monsoon rainfall in seasonal forecast. And Saha et al. Recently brought out I told about the potential predictability is 0.7. So that was the thing. And when I showed that graph with the Gaussian plot, it shows about 0.7. And Saha et al. Say that the way it is 0.7, I told that seasonal rainfall predictability comes from large scale time scale, from seasonal for the long-term variations of the SSTs, etc. Not from intra-seasonal or synoptic time scale. So what we thought is synoptic time scale and intra-seasonal time scale doesn't give you seasonal predictability. It's basically a part of internal variability. So basically it obstructs, it reduces the predictability. This paper is a very famous paper and also very controversial paper. So they told that the El Nino phenomena plays an important role not only on seasonal internal variability, it also plays an important role in short range time scale, also in the intra-seasonal time scale. Okay, even in synoptic time scale, there some number of synoptic system forming, a number of days with synoptic system. Similarly, the intra-seasonal time scale, active break cycles, etc., are also controlled by El Nino phenomena. So the predictability can come from also from short range time scale, basically from synoptic time scale as well as intra-seasonal time scale. So that's the concept which they told, and this is the new diagram which told. This is the diagram which I was mentioning about the potential predictability somewhere around 0.7, and this fellow is this group is saying now it's close to 0.8, but whatever it is. So whatever it is, but now what we know is our present skill is less than the potential predictability. That is very sure. Now, question is, what is the potential predictability? It's debatable. It could be 0.7, or it could be 0.8. So my point is that there is a scope for improving a present models to up to the potential predictability. And also, it's not 0.1. It's not 1. The correlation is not 1. It's only 0.8. Even if you assume 0.8, only 64%. So still some 36% is unpredictable. So that we should keep it in mind. Now, what are the issues with the coupled models? I have another 10 minutes. So one assay is told that this is a spatial map of correlation of CFS version 1, and this is the NMME model, and this is observation I showed earlier also. So the correlations of monsoon rainfall with SST is here. Actual observations, we know that this El Nino relationship is there, but in the models, the relationship is much, much, much stronger. That's one serious problem with the coupled models. And also, I told that there is a relationship coming from Indian Ocean. And this is a paper by Rajeevan group. And it's again from ensemble modeling system, which I mentioned about it. The model doesn't really pick up this is actual model, actual observation. You can see that the sign of monsoon rainfall over the region and sign of west decade Indian Ocean is same, the observations. But in the actual model, it's just opposite. So the models have problem of getting the Equino or IOD connection with the monsoon rainfall, or the relationship with the Indian Ocean, equivalent Indian Ocean and monsoon rainfall. The models have serious problem, except they say that ECMWF is ECMWF. Yes, somehow you can see that there's a red color here and a blue color here. This model is picking up some kind of relationship. Otherwise, all the coupled models have serious problem in predicting the Indian monsoon and equatorial Indian Ocean. This you can see that this is the correlation plot of observations, and 3.4, and this is from the model, and correlation is only 0.55. Here it's minus 0.66, much more. And this is from IOD. There's not much actual observation. There's not much correlation, but the model predicts over 0.61. Similarly, with Atlantic El Nino, so correlation is not that good, minus 0.4, but here it's very high. So that means the model doesn't really reproduce the realistic teleconnection patterns in the models. That's a problem. And this, again, we know that monsoon rainfall and the relationship monsoon rainfall and El Nino has been changing. There's a secular variation, correlations are pretty good, and then it went bad, then again went out. So this is the when the correlations went bad. So when the correlations weakened, that was the time Krishna Kumar wrote that famous paper in Science, 1999, that monsoon rainfall relationship is bad. So once he published paper, the correlation got strengthened again. So I used to tell my people, when something happens, immediately write paper, because we don't know what will happen after a few years. So when the paper was written, nobody knows that the correlation will get strengthened. So then what we know is, this may not be really a kind of a physical relationship. It could be a data problem. That means the samples which we use. And but there is what we should say that there is a kind of a secular variation of relationship, multi-decadal variation of relationship between El Nino and Indian monsoon. That we should know. But this model doesn't produce, everything is flat. That's a serious problem. The model doesn't really pick up the multi-decadal variability. And the models have systematic errors. It's a Chowdhury et al. Basically trying to compare all CMIP models from CMIP 3, CMIP 5, CMIP 6. And you can see the anomalies, the biases are all same color every year. So CMIP 6 also has the same problem. So instead of we develop much more improved models by CMIP 6, but with monsoon, the biases are still remain same. It doesn't really change. And so these are all these precipitation anomalies. What will happen is a dry bias here, but excess monsoon, more rainfall here, and less. And that is associated with SST anomalies, and very closely SST anomalies. The SST anomalies are here poor, and here it is more. So more SST is here, contribute to more rainfall here, and less SST is here, contribute to less rainfall over here. And if you really plot the Hohmüller diagram kind of thing, this is GPCB data, it goes up to the monsoon rainfall goes up to beyond 20 degrees north, but in the model it's all less than 20. That means the northward propagation of ITCZ, monsoon, so-called monsoon trough, monsoon rainfall, the actual observation goes up to central India, so monsoon trough, beyond 20 degrees north, but model just stops somewhere below 20 degrees. It doesn't really go. So that is a basic reason that we get dry bias there. The question is why these models doesn't really take ITCZ, or so-called monsoon trough, to north of 20 degrees. Whether it's a land surface temperature, so land surface process problem, so-called land atmosphere interaction, or soil moisture problem, or the lows and depressions which are forming over Bay of Bengal. So there could be a lot of reasons. And there are a lot of explanations also came why dry bias is really happening. But we really, frankly speaking, we really not understood the physics of dry bias, why it is happening. But we know that ITCZ is not moving beyond 20 degrees north. And so there is when you took water, I thought I will also take. I will also take water, if you don't mind. Okay, so so question is how we improve the model? What really we need to improve? So there are two concepts, two philosophies. One set of people say that you can improve the model skill, if the model mean rainfall or mean patterns are good. The model has a good fidelity of reproducing the mean patterns. If mean patterns are good, seasonal forecast skill is good. That's one theory. Another people say that no, mean is not very important. Teleconnections are important. Mean may be bought. You may still have bias and all these things. But if teleconnection patterns are really taken care, you can still expect more skill. Two theories. This is the first paper, is the Lee et al. 2010, very famous paper. Big people are involved. Bin Wang, Shukla, IISc, so many people are involved. So what they found is, they took some few models and they plotted the pattern correlation with the normalized RMS. You can see that If pattern correlation, that means mean pattern, is more, the RMS is reduced. You have this kind of relationship. Similarly, if you really plot mean skill with anomaly skill, the mean skill is, if mean skill is more, the anomaly skill also is more. Beautiful correlation. So when these people really wrote that if the model is good, you can expect the skill also is good, forecast skill. Then there is another concept. So we did analysis. What we found is that ENSO ISMR correlation and ISMR skill, forecast skill, if you really plot, if the correlation, the teleconnections are good, skill also is good. For somebody, the skill is, the correlation is 0.7 or so, less than 0.7, skill is very poor. But if the correlation is much bigger, negative correlations, then you get a much bigger skill. So what we found is that the skill is really related to the teleconnection pattern, how the correlations are. And this is another, I took it from Prashant, this is a recent paper which they are going to publish. And if you really plot the 11-year running correlation of skill, you get in the initial years, you can say that the skill is very poor. And then they picked up. And they say, and if you really plot the SST correlation between 3.9 monsoon rainfall, the correlations are pretty poor during this period when the skill also was very poor. So when this model, when the correlation got strengthened, really the skill of the model also has really strengthened. And these two are models. So the model did not reproduce this poor skill. So the skill model also had a poor skill here. But when the correlations are pretty good, the model picked up that correlations and skill also has improved. So what we are thinking now is the model should really reproduce the teleconnection pattern very well. This is just one example of the El Nino. It also could be related to Atlantic Ocean, could be also related to Indian Ocean. This is the paper, again, this is the paper by Prashant again. He's saying that in the second year, the first initial period, you can see there's a correlation is coming, sorry, this one. There's a lot of correlation in the second period coming from Atlantic Ocean, which the initial models were not really showing. But if you really take the recent periods, February, April initial conditions, the correlations are pretty good. So Atlantic Ocean relationship also should come very well. So what they said, the February initial condition skill is much poorer than April initial condition, mainly because the April initial conditions are able to pick up the correlation, the relationship of Atlantic Ocean with the Indian monsoon. So Atlantic Ocean also plays very, very important role. And if you really want to see other South Asian countries, how we do, these are the skills which we developed, which we prepared for Bangladesh, South Pakistan, North Pakistan, Nepal. Bangladesh is pretty bad. So seasonal forecast in Bangladesh is almost ruled out. So because we know Northeast Indian region is very bad, so it is close to that region. So basically they don't have, Bangladesh rainfall don't have a good relation with El Nino. El Nino doesn't play an important role. And whereas Nepal has. Nepal, many models are not so big, but there is some skill in the Nepal. To some extent, North Pakistan, but not in South Pakistan. So India, we are fortunate that our skill is much better than many other South Asian countries, and we should make use of it. And also important is another component could be clouds. In the so-called, the theme of your workshop is moist convection. The moist convection, the models may not be really good. And so this is a trim data, which shows how much percentage of convective rainfall happens, and also stratiform rainfall and shallow rainfall. The famous paper by Sai Krandi. And you can see that especially Northwest region, convective rainfall is much more than stratiform. But whereas over the whole Indian region, stratiform rainfall contributes much more rainfall but the model doesn't really pick up this difference. Of course, Partha has done a lot of work on that. This is a paper by Partha's group. So you can see that these observations, the percentage of rainfall fraction, and is almost close to convective rain as well as stratiform rainfall is almost same. But in the model, you see that it is much more. The model produced more of convective rainfall than stratiform rainfall. And when they try to improve the cloud microphysics, it is, especially the stratiform rainfall contribution has increased much substantially. So there are issues with the cloud microphysics and also the so-called cumulus parameters just in the model. Basically, moist convection is important. So in this concept, I think I want to highlight this famous paper, Robert House. So stratiform precipitation regions of convection is it a meteorological paradox? What he said that convective cloud and stratiform clouds are driven by same convective process. It's not too different. It's all same. I think you should read this paper to understand what do you mean by convective rain and what do you mean by stratiform rain. Okay, so this is I'll stop with this. It's a very what do you call it, a very impressive paper which has come out from Slingo and group. It's a big people are involved. Paul Gatz, Tim Balmer, Stephens, Thomas Stoker, who was in IPCC. They said that they are talking more of a climate change projections concept. They say even climate change projections when we make CMIP-6 or for any particular region, especially on precipitation, we get a scenario. Precipitation is going to increase, precipitation is going to decrease. But then they told that in the model, the precipitation is the serious problem. Okay, how a policymaker can really believe those climate change projections and take a policy decision which involves money, which involves a lot of investments, etc. So when we make climate change projection, that should be really of reliable. Our uncertainty should be much less when we really give the projections to the government. So she says, this group says that present CMIP model has large uncertainties, not really worth of giving to the policymaker to make a policy decision. Very strong statement they made. And they propose, and this is one reason, this is the correlation, this is when El Nino happens, what really observations should show. Less rainfall here, or El Nino happens, or Indian Ocean region should be less, and more rain here. But IPCC model 1, IPCC model 2, IPCC model 3, CMIP-6, all showing just opposite. When El Nino happens, this model show, for Indian Ocean region, we should expect a lot of rain. If this is the biases in the CMIP-6 models, even CMIP-6 models, biases are saying almost same, that means biases are not changed over the years. That's what they say. So if CMIP-6 models have still bias, just opposite of what a simple El Nino event has to cause, how we will believe a 50-year projection, 70-year projection, 90-year projection, and talk all this COP meeting, CFC, UNFCCC, big undertaking by Government of India. Are we really on the right track? That's what the question which we should take. I'm not questioning the whole concept, and there is no representative from the press here, isn't it? No, good. And okay, so what they say that the basic problem in the model is representing the so-called MCs. That is a serious problem. Convective systems is very difficult models, and this is the rainfall contributed by MCS system in the whole world. Mostly you can see that in the South Asian countries, most of the rainfall comes especially over the region here, is all contributing. So the model really doesn't really reproduce this MCS system. So for that, what you need is, they brought out a new concept called, and so if you really want to run a model with a very high resolution, it should be possible to represent. So you need a structure of this MC set. You see it, it's a very small time scale, spatial scale. A convective cloud is a very small one, 10 kilometer, 15 kilometer, and the structure is very complicated. It's not a simple ascending motion and descending motion. It's much more complicated than. So, and that models are really able to reproduce in a typical climate models. Answer is no. So you need very high resolution model in which you can explicit convection in a split form instead of doing a parameterization. So this is a paper by this group. It's a 5 kilometer resolution global model, and you can see how beautifully the clouds are reproduced. So they brought out a new concept called global K-scale model, 1 kilometer model. So they say that we all should work. It needs a lot of international collaboration. Ultimately, short-range forecast to climate time scale, you should have a global K-scale model. And you need huge computer. I put it in red color. It's almost, if you really want to 100 kilometer to 1 kilometer scale, you need a 2 power 20 increase in computing power. So in exa time scale, so exa scale, you need computing resources. But they say that's a way we should all work. And but there are again some papers. Immediately came 2 papers that come. That's not the right way of doing it. So I will stop here. I am not the right person to say anything about this K-scale model. I cannot even visualize it, at least from Indian perspective. We are moving to 5-kilometer model because thanks to Partha. I think that is good enough for us for the time being. 1 kilometer we'll think, maybe after 10 years. So I do not want to summarize because if summarize, what do you want to summarize? If story is over, you can summarize it. The story is still going on. Okay, the major challenges seasonal forecast still remain. One option could be to wind up the seasonal forecast efforts, which UK Met Office tried to do it a few years back when their forecast went bad. There was a lot of criticism. They all said that we are going to stop. Thanks to India, we are not doing it. We never stop. So my point is that we should not do that kind of act. India should put out more efforts to resolve the gray areas, improve monsoon forecast. I personally feel there's a lot of scope for improvement of seasonal forecast for Indian monsoon. With that hope and scope, I'll stop here. Thank you. If you have any questions, I'll be happy to answer.
Thank you, Dr. Rajeevan. We have some time for questions.
Before that, I'll tell you another story, if you don't mind.
Sure.
2007, when we introduced the new ensemble forecasting system, it was reviewed by people from Indian Institute of Statistics from Bangalore. Sulochana Gilles helped me to do that because we wanted to make sure that the forecast may go wrong, but the system which we are going to announce it, we are going to put in operation should be scientifically sound. It was reviewed by two big teams in IISc. The first 2007, we introduced the first forecast. Actual rainfall was little off. It was not so good. I remember Gilles was the secretary. He called me. He said, "Your so-called famous model did not really give a good forecast." But I'll tell you, Times of India wrote a central page editorial saying that IMD has come with a big fanfare and brought the model and all failed. And they wrote a sentence, "The man who developed this model, me, doesn't know the basics of meteorology." Basics of meteorology. They wrote, I kept that editorial for many years. 2008, forecast was on the dot. Our forecast was on the dot. We gave 103 and it became 102. I told that's the right time to leave IMD. I left IMD and joined ISRO. That's the story. So we IMD people, easy to write paper. Sit in a computer, write papers, publish it, H-index, everything is good. But when you go to the public and tell that, you take your neck out and tell to the government, and government takes a very important decision based on your forecast. It has a lot of stake. It can put down your stock exchange. RBI can take a wrong policy based on your forecast. Your seasonal forecasts are very, very, very important. So you take a risk from your career and put your neck out and say that this is a forecast. And you stand with that forecast. And when the forecast goes out, of course, you have to give an explanation. And unless short-range forecast, which you can verify it in 2-3 days, I give a forecast, day after tomorrow it will not rain. When it rains, of course, the verification is done. Here, you issue a forecast in May and wait till 30th of September. You can just think about the mental agony a forecast, monsoon forecast had. That's all. Thank you.
Yeah, thank you.
Thank you.
Thank you. That does
not mean that you should not issue operational seasonal forecast. You should also get involved in seasonal forecast. It's a country's need, and you should work on them.
Thank you. That reminds me of one slide Sulochana used to show, which had a quote from the Minister of Economics, I think
Pranab Mukherjee. He told Monsoon is the finance minister.
Monsoon is the real finance minister.
That is true. That's true.
Yeah, the floor is open for questions.
No questions on finance, but.
Very informative talk. My question is, are seasonal forecasts able to capture the spatial variability of extreme rainfall events? What I mean is, let's suppose we have a seasonal forecast, and over one region we see anomalous increase in the rainfall than the climatology. So can we conclude that this year, that region is going to face the extreme rainfall events?
No. It's very difficult to say. So what IMD gives is early days we should give one number, 106%, 104. We don't tell them that where you can expect more rain, less rainfall. Now they give a probability forecast, a spatial distribution, where you can expect normal rainfall and more rainfall, less rainfall. We give in 3 categories, equal probabilities of 0.3 or so. But then the skill is not that good. If you really go to a spatial scale, some years it works very well. Because the spatial pattern of a particular year, assume that same boundary condition, El Nino, IOD, spatial distribution of particular 1 year will be different from another year. It will not be same. So monsoon, frankly, the monsoon is not unique. One monsoon is not the same of next year. If it was so, it was very easy for us to do it. Unfortunately, it's not. So the spatial distribution of anomalies, even in a particular drought year, it can vary. We know very well Northwest India, Central India is the place where normally it affects, but it can vary.
Thank you.
Other questions? If not, maybe I'll ask a question.
Yeah.
My question is about the dry bias. It's been there in climate models as well as CFS versions of models. So Arindam gave a kind of talk where he talks about the moisture flux from western and eastern boundary and links it to the north-south surface pressure gradient. So can we kind of attribute this dry kind of bias to the large-scale processes and especially the
It should be related to large-scale process, not the local condition. It should be related to large-scale process. But exactly, I know the paper. I was just reading a few days back. You are other? No, you're not. You're not.
Yeah,
I remember
the fan of that paper. Yeah.
I remember the paper. Yeah. So, but the process should be a larger type, a spatial scale. It may not be a local. But local effects also play important role for some soil moisture feedback, land surface feedback. So we don't know how the things are happening.
Right. So in some sense, the seasonal bias, can it be kind of linked to the larger scales?
Of course. Yes. Okay. The seasonal forecast skill is completely influenced by large scale patterns in the models. Models reproduce the large scale teleconnections and mean condition. The forecast skill also. But also we should know that there is a limit in predictability. Right. We should not expect too much. But there is a scope for improvement. That's all we should expect.
Yeah, my other link question was, please, maybe you get the preference. I have asked one question.
I have a very general question on models. So what is your thought on statistical versus climate models?
Statistical models, I'm not saying that they're not good. They're good. Especially if you don't have a dynamical model, statistical model is good. So, but the answer is it cannot do what dynamical models can do. So for example, dynamic model can give you a larger spatial information and also the temporal information. For example, June, how it will be, July, how it will be. Whereas statistical model, if you really want to develop a model month-wise, the skill will not be that good. Statistical models are good, for example, for monsoon. I'm talking about monsoon forecast. For an all India perspective, it is good. Still it is good. I'm saying still it is good. The model, the seasonal forecast, IMD's statistical model is still doing very good.
Right. People are trying to make the statistical model dynamical linear models or dynamical quadratic models. Like using some techniques, there are Kalman filter, there are different techniques they are including in the statistical model. So that is where, like, when I was writing my paper was on statistical model only. So the criticism was, okay, statistical model can work good, but the relationship between independent variable does not vary over time, that does change over time or update over time. But then we tried dynamic linear models as well. So far, like on the forecasting of the drought, it worked well for our area, but not as well as the climate models.
I keep doing it. That's all I can. Keep doing. And what you do is correct. Keep doing. See, there is no, I'll tell you, there is no one good way of doing it. There could be many ways of doing it. So statistical, if it doesn't really work, nowadays people talk about AML, you can even develop instead of a simple linear model, you can develop a non-linear model using some machine language system, neural network, for example. So this is scope. Yeah, you wanted to ask something?
Yeah, no, so I wanted to ask you about so teleconnections versus having mean right and hence the variability right. Are they necessarily disjoint or maybe simultaneously?
That we don't know. So we assume that they are disjoint. So but the models, for example, models who are not really good in mean also have a problem in teleconnection. Quite possible. Quite possible. But we are not really. It's a gray area. It's a this is problem which we can do it. So we assume that there are one set of theories, philosophy saying that only you don't worry about teleconnection, you worry about mean. And another theory is they say that don't worry about mean, it can have biases, but teleconnection pattern should come to. But my point is that if mean is not good, teleconnections also. So I did not show the diagram. I have a diagram. So it shows that if mean is not good, the models also will have a problem in teleconnections. So my perspective that both should improve. So teleconnection can improve if automatically improve the fidelity of the model. If mean pattern improve, automatically teleconnections will improve. Because see, teleconnection nothing but where the heat sources and sinks. If it's in the correct proposed places, it will work. For example, El Nino connection, where the heating is there, where the sink is there. So the mean pattern means the correct sources and sinks will be placed at the right time, right place. If that is misplaced, your teleconnection also will go wrong. It's very simple physics, isn't it? So that's a hypothesis I make, but we are not really worked on it. They should do.
So I think in this talk you focused also on the fact that there's some large connections with, for example, ENSO, and you also reminded us of the title of this program, which is related to moist convection. Do you think it's also possible to try to improve these seasonal timescale predictions with sort of upscale effects of improving the moist convection? You talked this a little bit in the end with the stratiform versus convective thing, which I think was interesting. So do you think there's hope?
It should have. My gut feeling is that it should work. People like Partha has done it for short-range forecast. It improves the moist convection. It improves the intra-seasonal variability, northward propagation of ITCZ, everything. It is all improving. But not very systematic studies have been done by improving cloud physics or cloud microphysics or cumulus parameterization by seeing the skill of seasonal forecast. I'm correct?
But that Monsoon vision paper of Surya, they actually analyzed all the hindcast, which includes the modifications in clouds, convections. He was showing a slide, possibly, and he showed that there is substantial 50-60% improvement from the default CFS.
So, but where is attributed to the clouds or attributed to the ocean?
Clouds, huh? Yes.
Attributed to the clouds.
Clouds. So this paper is that same BAM's paper. There is a table where he has demonstrated. Yes.
It should.
Yeah.
Sure. So
there is upscale effect. You can read that paper. Yeah.
Again, it's same, putting in the heat sources and sinks at the right place. So that is very important. So unless that is improved, seasonal forecast, you cannot expect seasonal forecast.
Showing that's 1886 to 1952. Is it that same lady, Sarah Carson, who came on Fulbright and
Yes. Yes. She
Okay.
came to Pune. She talked to.
So is it a paper or is it?
It's a very famous paper. It is published in not in typical meteorological journal. I can send it to you. It's a very huge paper.
Okay.
A very huge paper. But she wrote very well.
Okay. She told I will stop at 1947 or 50 when India gets freedom. So
I see.
I mean, she just wanted to explore pre-independent era of how is the forecast.
Yes.
But I think she has gone.
She has gone up to 1953. The 53, the Norman's review paper is there. She has stopped it there. But she little mentioned about our recent initiative, statistical models, etc.
Okay.
She quoted Kilka, she quoted me. And,
Okay. Yeah. Thank you.
so she remembered us. So it's the same Sarah Carlson. Okay.
Well, if there are no more questions, let's thank Dr. Rajeevan again.
Thank you.
Thanks a lot for coming all the way and giving this plenary lecture.
Thank you very much.